Good afternoon. Good afternoon. Okay, let's try it again. I'm Joan Fickey. I'm the interim provost, and I have the great good fortune of convening this meeting and then allowing another faculty member to do all the work. So it's wonderful to be here. It's delightful that San Jose State has this series. I understand it originates in the provost's office. I'd like to take credit for it, but I can't. But it's a wonderful idea because, after all, what we do here is knowledge. We learn about things, we teach about things, it's in our heart, it's in our minds, and so to participate in an experience like this is really why we're here, and for me personally, it's really a joy. So I want to thank San Jose for creating this opportunity, and shortly I'll introduce our guest, and I want to thank him for what he's going to be sharing with us today. The lights are actually going to go off after I stop speaking. It's going to be like Hayden Planetarium, right? Okay, that's what they told me. So this is the University Scholar Series. This is our first guest. And I want to make sure, I normally don't read these things, but my discipline is public health, so I don't have as much facility with some of this language, and I want to make sure that it's accurate. So Professor Aaron Romanowski is an associate professor of physics and astronomy here at San Jose State University. He was an undergraduate in physics at UC Santa Barbara, and he did his doctoral research in astronomy on dark matter, gravitational lensing, and supermassive black holes. Are there moderate massive black holes? Okay. He did that at Harvard. I'm not going to hold that against him. He then crisscrossed the globe in search of exciting galactic data. Again, I need to ask, I think all galactic data is exciting. Okay. And he did that in the Netherlands, he did that in England, Chile, and UC Santa Cruz, and again, we won't hold that against you. He now works at the interface of telescope observations, computer simulations, and machine learning to understand the nature of dark matter and the origins of galaxies and star clusters. I'm a little overwhelmed. He leads a team of students, and some of you have already shared that with me, and you have knowledge of the work that he's done with his students, and I believe Aaron is going to talk a little bit about that today. So he leads a team of students at San Jose in search of the most extreme stellar systems in the universe, recently discovering the densest known galaxies, and now pursuing, I don't get this, the fluffiest galaxies. What's a fluffy galaxy?
That's what I have to show you.
Okay, I have to wait. All right. And that fluffy thing really got to me. He is co-director of CalBridge, a program to support CSU undergraduates in pursuing doctoral studies in physics and astronomy. One of the reasons that I chose to spend a year at San Jose State was, some of you know I did some consulting last year, but I think it's fair to say, blown away by the quality of some of the work that is produced here and the mission of San Jose. And I think that our guest here today reflects that dramatically, and it's delightful to be able to be in this position, having done none of the work to organize this, to present someone who does this marvelous work to a group of folks who are curious about understanding it. So my pleasure to introduce Professor Aaron Romanowski.
I'll turn on the mic. Well, thanks after all that introduction. I'll try not to disappoint. Great to see so much turnout. Thanks for coming. How many people are here to hear about dark matter? How many people are here to hear about black holes? How many people are here for the food? Okay, so I'm going to not go over all the different things that we just heard about, but I'm going to start from the beginning. This is something that hopefully everyone's seen at some point in your life. This is what? Anybody recognize it? Well, so the telescope down here, what's the beautiful pattern up in the sky? That's the Milky Way. Okay? In the Milky Way, Galileo, and of course if we see this with the naked eye, it doesn't look that beautiful, But Galileo was the first one to turn a telescope on it and see that it's not just a milky band across the sky, but it's actually made up of innumerable stars. Well, we can count the stars now, and we have an approximate number. There's about 100 billion stars in the Milky Way. This is sort of a wraparound view of the Milky Way all around the sky, and it's a band. It turns out we live in a disk-type galaxy about 100,000 light years across. That means it takes light, which goes at a tremendous speed, 100,000 years to cross the galaxy. This is what the Milky Way might look like if you were to zoom out to the outside of it and look back. It's got this beautiful spiral pattern. This is a different galaxy, or it's an artist kind of composite. And we don't live at the center of the Milky Way, and I'll talk about that a little bit more. We wouldn't want to. We live out here in between a couple of spiral arms, out in the, kind of midway out in the suburbs of the Milky Way. So the Milky Way is not the only galaxy in the universe. This was something that was discovered about 100 years ago in some great debates of the early 20th century. This is the nearest galaxy, major galaxy called the Andromeda Galaxy. It's the farthest object you can see with the naked eye. If you know just right where to look and the skies are dark, you can see this. It's about 2 million light years away. And it is also surrounded by smaller galaxies. These are dwarf galaxies. This is called that's the Andromeda Galaxy. This is a dwarf elliptical and a compact elliptical. So I'm going to come back to this because a lot of you may have heard about these giant spiral galaxies, maybe the giant ellipticals, but you might not have heard about these dwarf galaxies, which actually outnumber the giants. There's a lot more of the small ants. Think of like all the small ants in the world versus the larger insects. It's sort of like that hierarchy. And this is another example of an even fainter dwarf spheroidal galaxy. So each of those galaxies contain from 10 million to 100 billion stars, depending on the galaxy. So how do we study them? Well, the classic mechanism for astronomers until very recently, the only mechanism really was light, until the advent of gravitational waves. So anybody name that telescope observatory? It's the Hubble Space Telescope. Hopefully you've all heard of that. Beautiful instrument that's been up there for a couple decades now. That's one of the most famous pictures it's taken. This is one here. This is the Lick Observatory. So once the blinds go up, you might be able to, I'm not sure from the second floor if you can see it, but if you look out from the higher floors of the library, you'll be able to see on Mount Hamilton here on the horizon, you can see this observatory. It's a very famous, important observatory, the world's first permanent mountaintop observatory, founded in the 19th century. And it's got this laser, which I'll come back to later. Even bigger telescope, these are the Keck telescopes on the Hawaii, the world's most powerful optical telescopes. So the question is, what do we do with these kind of telescopes on the ground? The Hubble takes these beautiful images from space. What do we do with these? Turns out, we typically don't take pictures. And we often have this question, say, at the Keck Observatory, where's the pretty pictures from Keck? Well, that's not what we tend to do. We do something called spectra. So I'm going to have to unpack a little bit why we do take spectra and why we care about them. Okay. So there's a prism, which if you put sunlight or white light through a prism, it disperses out the rainbow colors, and it looks like this. So this is a view of what the sunlight would look like in that rainbow, but when you look at this carefully in a lab, it's not just the rainbow, but there's these dark lines in there, and you can see these readily by eye if you've got an instrument that'll look at that. That turns out, and I'm going to say for reference, wavelength is shorter wavelengths to the left and longer wavelengths to the right. These are sort of like wavelengths on the ocean. It turned out it was discovered in the 19th century that these lines correspond to lines that you can see in a Bunsen burner in the lab. If you vaporize salt, for example, you see this line, which corresponds to the element sodium, and it matches up to a dark absorption line. This emission line is an absorption line in the sun, which was a miraculous discovery, that turns out the sun is made out of the same stuff as on Earth. Okay, there's sodium. Turns out that there's hydrogen lines, magnesium, and there's lots of other elements that you can find in there. It turned out there was something else found in the sun called helium, which we didn't have on Earth, which is why it was named after the sun, Helios. It thought that maybe this was some special substance on the sun. It took a few decades before that was actually discovered on Earth, but that's where the name helium comes from, because it was first discovered in the sun. So this is one of the reasons we do spectroscopy, is we find out what other objects in the universe are made of, since we can't go up with a shovel and dig them up or take samples back to Earth, with a few exceptions. Okay, that was the helium discovery. The other thing we can do is measure what's called Doppler shift. So if you've ever heard, you'll hear Doppler shift in terms of sound in daily life. So I'm going to apologize. I'm going to make a very annoying noise here. And let's just start swinging this around. Can you hear the difference? As it comes toward you, the pitch is higher. As it goes away from you, the pitch is lower. And that's what you hear when a train goes by or a car. And that's called the Doppler shift. And what happens is the motion of the object effectively compresses or decompresses the waves in front or behind it, makes it higher or lower pitch. It turns out light will do the same thing. If I swing this around at close to the speed of light, two things will happen. One is that the light will change wavelength, and the other is that I probably break something very badly. So when the light goes to a lower frequency or a longer wavelength, we call that redshift, and it means the object is moving away from us. And here are some examples of redshifts. You have these, again, these spectral lines at characteristic positions, the blue, green, and the red. And as the object moves, it shifts those lines around, and you can actually see some subtle color differences as well. You can measure that shift and measure how fast the object is going. So we call that red shift or blue shift. You might have heard those terms before. So there's the two big reasons we like to use spectra, because you can determine the compositions of objects, and you can determine how fast they're going. Well, why do we care about how fast they're going? Let me get to that. Here's now I'm going to have to pop this out, a video, see if this works. Okay. Oh, is it safe? I hope so. Except it's the wrong one. Okay. So this is a video taken by a European observatory called, space telescope called Gaia. And it's using data to reconstruct the motions of stars in the Milky Way. So you saw the Milky Way before. Well, every star, every object in the Milky Way is moving. It's just on human timescales. It's very hard to tell. Well, the satellite can now measure that. And I hope you can see these measurements of the stars. The clock is running very quickly now, hundreds of thousands of years in the future. You might be able to see there's a bulk motion in, which way is it all moving? Left to right? I can't tell from my vantage point. I think it's moving more toward the left. It's not that the galaxy is moving, it's that the Earth is moving, and the sun with the Earth around is moving relative to the galaxy toward the right. It makes the stars appear to move to the left. But every star moves in a little different direction. So we can use that technique, let's see if I can get back to the PowerPoint, to measure the speed of stars going around the Milky Way. And so why is this important? This goes back to Isaac Newton, who made this connection between objects like apples falling on the Earth and the moon going around the Earth. That might be the same gravitational force. Power of gravity, why not as high as the moon, said he to himself, whereupon he fell calculating what would be the effect of that supposition. So two things here is have a great idea, that's how science works, a great idea, and then also work out the details. And the third thing is actually test the details. It turns out, this is something I only heard about recently, he tried out his gravitational calculations, and it turned out to not fit the data. And he kind of threw it in the trash can for about 7 years until it turns out the reason was because we got the size of the Earth wrong. This guy called Picard invented the sextant, which recalibrated the size of the Earth, and then everything fell into place. So he did those three things: the idea, the theory, the calculations, and the testing against the data. And now it turns out it all holds together. That's the same gravity pulls the sun around, the sun around the galaxy, the moon around the Earth around the sun. It's this universal law of gravity that governs the whole universe. And I won't get into physics here, physics equations. I'll just say the basic rule of gravity is it's called an inverse square law, where the force of gravity varies as 1 over the square of the distance between the two objects, or the orbital speed goes as 1 over the square root of the mass. So I won't go into the details. Let's just say that if you can measure the speed, if you measure the speed of of the moon around the Earth, you can measure the mass of the Earth. So that principle we can use all over the universe to measure masses of objects. So one of the ways this was done was in the 1970s, various astronomers led by Vera Rubin measured the speeds of gas and stars around galaxies and discovered that they were going too fast, that those galaxies ought to fly apart. What that means is there's some kind of a missing mass, and became called dark matter. And so we have this picture here. You can't take a picture of dark matter by definition, but if you could, it would look something like this. You've got this galaxy like the Milky Way embedded in this great mass of dark matter we call a halo, but it's sort of a filled sphere, not so much like a circle or something like that. So what is dark matter? Well, I say dark matter is a variable concept. It's basically anything we can't see yet. Okay. Historically, there were other types of dark matter that became non-dark matter. Includes the planet Neptune. There was a gravitational force detected from this unseen planet, which is eventually detected. Gas that was at first invisible. Neutrinos were a type of dark matter that eventually became detected in the lab after many decades. Something called, but the question is, what makes up this dark matter that surrounds galaxies? Now, there's a couple of different candidates. When I was in grad school, one that was still possible was called MACHOs, for massive compact halo objects. These could be dwarf stars, planets, black holes, SOX, any kind of what we call macro material object that's kind of floating around in space that has mass but you can't see it. Turns out those are ruled out by various experiments. So the main one we're left with now is called weakly interacting massive particles. Okay, so astronomers and physicists do have some sense of humor. These are things like supersymmetry predicted particles, things that I don't quite understand myself. And other things that are coming into favor now, like ultralight axions, sterile neutrinos, other exotic particles. It's not crazy to think that these things exist. Like I mentioned, neutrinos were something only discovered within maybe about 50 years ago. And there could be other particles out there that are very difficult to detect. So it's not outrageous to have these unseen particles. In fact, some theories predict these. And the search is underway. When we really are clear about what's going on with the dark matter, we'll detect them in the lab. There's various underground detectors right now working on trying to detect these. So stay tuned. Hopefully we'll find the dark matter soon, exactly what that is. But let's just say we see its effects. We see its effects on galaxies, and it's not just a curiosity, this missing matter. It turns out that they're necessary. So first of all, here's the picture. The universe appears to be made up of 85% dark matter and 50% normal matter atoms that we're familiar with. And that dark matter is necessary to pull the galaxies together, which pulls the gas into stars, and the stars blow up, recycle, and make planets, and the planets make us. So the dark matter is really necessary for us to be here. So I'm going to show a video which illustrates, this is a computer simulation of the universe on some very large scales, where our galaxy would be kind of small size in here. And this is the beginning of time. The universe is kind of diffuse. And this is imagining you can see the dark matter, which you can't. And it collapses under gravity into these great filaments. And now I'm going to put in lighting up the gas and the stars in these and zoom in to a galaxy forming. And the gravity pulls the gas along these dark matter filaments to form galaxies at the centers of nodes where the gas collides and forms stars. And the galaxies collide as well and merge and form bigger galaxies. And this is the ongoing, we call hierarchical structure formation of the universe. This is a continuing process. The universe continues to evolve. Now this is just showing what you would actually see with your eyes, the light from the stars, back to this gaseous view. And maybe I'll skip ahead to the end, say like eventually things settle down and we get something that looks like the Milky Way today. So this is a picture, a pretty clear picture of how galaxies form. And the nice thing is we can actually we can see into the past directly with the finite speed of light to see galaxies forming and kind of confirm this picture. So there's another kind of dark matter at the galactic center, which I'll show a picture of, a video of. This is a reconstruction from using the Keck telescope to measure orbits of stars around the center of our Milky Way galaxy. And they move around very quickly, some of these on time spans of decades. So normally stars take millions of years to go around the galaxy. Here in the center, some of these go around in human lifespans that astronomers have seen stars go to complete orbits now. And what that implies, again, you can measure the mass from the speeds. There's a huge amount of missing mass, invisible mass, right there at the center of these orbits. And that is a supermassive black hole at the center of the galaxy. The movie speed here is 2 years per second. So it turns out this has a mass of 4 million suns, all combined into this giant black hole. If anyone's seen the movie Interstellar, it's like that black hole, the gargantua black hole. And that's why we don't want to live at the center of the galaxy, because of that black hole being there. So, okay, that's kind of leads into the next thing. I talked about galaxies. I talked about these mysterious invisible black holes and the dark matter. It turns out we're not done discovering galaxies even, much less these other things. So I was involved with a group where we found in 2013, this is a giant galaxy, elliptical galaxy here. It turned out this thing here we discovered was another very miniature compact galaxy. We call this an ultra-compact dwarf orbiting this galaxy. So it was a new class of, it was a part of a recently discovered class of galaxies, the ultra-compact dwarfs. This is the densest example. So this has 200 million stars, only 160 light years across, so these stars really crammed into a small space. And this was the densest galaxy known at the time. So when this came out, it seemed, I talked with students here at undergrads at SJSU about this, and we thought, well, this is fairly easy to see. I mean, you can just look at that picture and see that's there once you know what to look for. And a couple of the students went out and looked. Now, we don't have access here directly at SJSU, our own like giant multi-million-dollar telescopes, but the nice thing is that there's a lot of public data available now on sort of national, international basis. One of the most famous ones called the Sloan Digital Sky Survey, operating out of New Mexico, and has made all the data available online that you can actually go onto your phone. You can literally make this discovery on your phone now once you know what to look for. Pull up like the app to look for these things. And they found this object. Each of these, this is Richard Vo and Michael Sandoval, now graduated a few years ago. Each of them found a really interesting object. One was what Richard found was the new densest galaxy called M59 UCD3. And then Michael found something that was even more exotic. We're calling it a hypercompact cluster. It's even denser than that. We think it might be in its own category. Maybe the only one of its kind known so far. So what we've done is gone off and done a lot of follow-up. Richard went out to Hawaii to try to observe his object. And one of the methods we use, I showed this laser before, pioneered here at the Lick Observatory. Now this is used at every major observatory. These lasers are called an artificial guide star. They measure the turbulence in the atmosphere that's like a mirage that hinders our ability to see things clearly. And what that allows us to do is look into the center of this galaxy and search for the effects of a supermassive black hole. This is using the Gemini telescope on the Big Island of Hawaii. And here is a spectrum. This is actually the actual spectrum, and there's a sodium line, which I mentioned earlier. We can measure the widths of those lines to measure velocities, again, like I showed, and this is a reconstructed velocity map of this galaxy at the center. And the color bar here is that higher speeds, or you can think of hotter temperatures, they're faster orbits at the center of that galaxy. So most of the galaxy is pretty similar color, except right at the center, there's these very fast-moving stars. And what that is a signature smoking gun of a supermassive black hole at the center of that galaxy. So that supermassive black holes are thought to exist in every large galaxy, giant galaxy, but when you get down into these small things, it was not clear that that would be the case. Here's an artist's picture of what that might look like at the center of the galaxy. You have this very dense galaxy with a black hole at the center, and there's a gravitational distortions or lensing effect from the gravity of that black hole. It's a general relativity prediction. So this galaxy has a black hole weighing 4 million solar masses, which is the same as the center of our galaxy, but this is a much smaller galaxy. This tiny little galaxy has a black hole at the center the same size as in our giant Milky Way galaxy. So how can this be? Well, we do have a nice handy story for this. It's got a lot of evidence for it. And I'm going to show this as a video. So Michael Sandoval is one of these students, not only went out and made this discovery, but he also went and made this, I think, really cool video, a simulation of what we think happened. So what we think happened is that there was a larger galaxy, well, kind of an intermediate-sized galaxy orbiting this big one, and it fell in through gravity and become stripped apart by gravitational tides. But what it had originally was this compact nucleus at the center, which is going to survive. So it's sort of like you have a cherry. You eat the cherry, but there's this cherry pit that's left over that is harder to chew. And it's harder for this big galaxy to chew up that little compact region. And that's left behind. So over a span of a few billion years, all these other stars disperse and become hard to detect. But this little cherry pit is left behind. So at some point it's going to freeze. And we'll zoom in. The real image. Now we're going to imagine we could zoom in even farther and see the black hole at the center. And now imagine we're on a planet at the center of this ultra-compact dwarf orbiting the black hole. And that's what the night sky might look like. So instead of on the Earth, we see a few thousand stars from the naked eye if you're in a dark space. Here you'd see about 1 million stars with the naked eye. be a spectacular place to live. Also probably a dangerous place to live. Okay, so Richard and Michael set the bar really high for students to follow, so everyone's got some, a nice act to follow, but we've got a group that's been working for years on doing more follow-up discoveries. These are some more objects that students in our group have found. Here is kind of a recent version of the group with some of the students all of them have found some of these objects and published, some of them have so far been published in research journals. And we're also forming a band called Ultra. Yeah, we don't have enough instruments yet, but yeah, stay tuned. Okay, so the question is, we found these densest galaxies, or what else might be lurking out there? That's what's fun about astronomy. We're kind of in the golden age. We keep discovering new things. Okay, does anybody know what that is, that symbol? Subaru, from the car. Why? These are actually stars, the Seven Sisters. So it turns out Subaru is the Japanese name for the Pleiades constellation. So I don't know why the founders of Subaru are fans of this constellation or whatever, but that's what it is. And there's also a big telescope on Hawaii. The Japanese have a huge telescope called the Subaru telescope. So you might think, oh, it's sponsored by the cars, but it's not. It's just that's the actual astronomical constellation. Anyway, so here's an image we were looking at with the Subaru telescope of some patch of the sky. You can see there's some stars in here in the foreground, some galaxies in the background. Well, it turns out if you look a bit deeper, you start seeing more stuff pop out. You see these faint smudges. So the deeper you look with these photographic exposures, the more new things you start finding. Okay, faint dwarf galaxies. So I'm involved with a project now called Project Dragonfly. I came in kind of late on this, but the founders, they had this great technique where they, instead of going out to these giant professional-grade telescopes, they use off-the-shelf telephoto lenses used by sport and nature photographers with this kind of pioneering anti-reflective nanostructure coating, which cuts out reflections and allows it to be a lot easier to detect these faint objects. And one of the things this group did was find a whole new class of galaxy called the ultra-diffuse galaxies, which I'll show a picture of in a minute. They're followed up with all sorts of other instruments, including the Hubble Space Telescope. There's an example of these galaxies, which are so diffuse. These are the opposite of those compact ones. Now these are the fluffiest galaxies I'm talking about. They're so diffuse that you can see other galaxies through the backside. Okay, there's the tenuous stars all spread out. So if we go back to the Andromeda galaxy I showed as a point of reference, and remember these are these dwarf galaxies around it, and if you imagine putting an ultra-compact dwarf next to it, it looks like that. And if you put one of these ultra-diffuse galaxies next to it, it would look like that. And actually, I've kind of upped the exposure time here, so if you really put it up, you wouldn't see it. It'd be so faint, but just so you can see it, there it is, this gigantic thing that's spread way out, the size of a giant galaxy, but 100 to 1,000 times fewer stars. And so we're still puzzles and arguments now, these new discoveries about what these actually are. It could be that these have dark matter halos like our giant Milky Way or Andromeda, but just few stars. That's like a failed Milky Way. Or it could be it's just a dwarf that got splashed out to a large size. This is sort of like, in biology terms, you imagine like having all these basic classes of mammals. I think those are classes. And imagine finding a whole new class of mammals that after all these years. That's sort of what it's like for astronomers, is finding this whole new class of galaxies. So again, here's what the night sky might look like from the Earth. Here's what it might look like inside an ultra-dense or ultra-compact dwarf. Inside an ultra-diffuse galaxy, you might see just a few stars. You might not even realize you're in a galaxy. The universe would just look empty. Okay, so back to the physics and back to measuring the mass. So now we want to say, okay, how much dark matter do these things have? We go back to the telescope and take spectra and measure the speeds. This first one that we measured, it turns out the stars are going at incredible speeds for a galaxy this apparently faint, 100,000 miles per hour, which is close to the speed of stars going around our own galaxy. And it implies a huge amount of dark matter. I think I skipped over it quickly earlier, but normal galaxies have maybe 100, 250 times as much dark matter as stars. These ones have over 1,000 times as much dark matter as stars, so they're very dark matter dominated. So this kind of goes to what I mentioned as maybe being a failed galaxy. We call these galaxies that died early, became ghosts, and stopped forming stars, but they still have a lot of dark matter. And it's not clear why that would be the case.
Can I ask a quick question?
Yeah.
So you said the ratios, but compare with for normal dwarf versus this dwarf?
Oh, it's about that ratio. So it's about whatever that is, about 6 times as much mass, maybe 10 times as much for some of them.
But the absolute amount of dark matter, number of kilograms of dark matter, is about the same for the two galaxies?
No. So this is so for the same 2 galaxies, a dwarf with the same amount of stars, then this thing has maybe 10 times as much dark matter as the other one, the absolute amount. Yes. And in fact, the point, one of the points of contention is they might have so much dark matter that's the same amount as the Milky Way has. And I think that's maybe an extreme possibility. We're probably not quite that extreme, but it would be like these giant Milky Ways that mass dark matter halos that also live around these. So this hit the news. CNN saw it as dark twin of the Milky Way. That's kind of exciting discovery. Also, there was some other news on the internet that I'm still not quite sure about. I guess I'm the astronomer from Russia, and I don't know how dark matter turns into devils, but anyway. If anyone's a fan of this news feed, let me know. Maybe you could explain it. Okay, so then we went out and we recently, we found another one of these things nearby, ultra diffuse galaxy, which we call the blob as our initial name for it. And it was very nearby, so we studied this in detail. We're expecting to discover a lot of dark matter around it. And it turned out the stars are going extremely slowly. It's sort of the opposite. It goes about as fast as this. Anybody recognize this? Yeah, that's Elon Musk's Tesla Roadster. That's about as fast as that Roadster goes around the sun. It's a really slow speed. Okay, and that means that this galaxy shows no evidence for dark matter. So I remember there was this big surprise back in the 1970s about all this excess dark matter on galaxies. That becomes now conventional wisdom. Now here we are back to pre-1970s, where this is a galaxy with no dark matter. So this has an incredible amount of controversy that astronomers don't like this result, and with good reason. I don't blame them. It kind of turns things on their head. So we're trying to understand how this galaxy doesn't have dark matter, apparently, and trying to reconfirm the result. But one of the interesting things about it is that having no dark matter seems to demonstrate that dark matter exists. So until we detect dark matter in the lab, there's some suspicion that maybe gravity just doesn't work the way we think it is, that maybe general relativity changes, there's extensions of gravity that change on very large scales that make it look like there's dark matter, but it's just gravity doing something weird. Sort of like you have Newton's gravity, they have Einstein's gravity, and there's this post-Einstein gravity. But that would say that you can never get rid of these funny gravitational effects. So here's a galaxy that got rid of it. So in a way, it's a way of proving, by having no dark matter, it's proving that dark matter exists. Because you can take dark matter out of the galaxy, but you can't take gravity out of the galaxy. Anyway, so here was the news coverage of this discovery in The Guardian, Galaxy Without Any Dark Matter, and Fox News. So it was just interesting to see that here was something where The Guardian and Fox News could agree on something. Okay, so now we've got this situation where you've got these things, that these curious galaxies that by eye, optically, they look the same. This is the blob, this is this dragonfly galaxy. But when you look at them in detail with spectroscopy, this one is almost all dark matter. I call that the shadow galaxy, and this is almost all stars. I call that maybe the vampire galaxy, because it doesn't have a shadow. Right. So this is what's fun about astronomy now, is that we keep finding new things that nobody even imagined or predicted. It's a nice quote from Shakespeare that I think about sometimes. More things in heaven and earth, Horatio, than are dreamt of in your philosophy. Keep finding new exciting things, and students have a great role to play in this. And so where do we go next? We go back to the telescope, and there's some of the students from San Jose using the world's largest telescope to go and follow these up in more detail and get better data. And hopefully you might see another student discovery in the news before long. Thanks for your attention. I think we're open for questions now. We have a little time.
Can there be stars that aren't attached to galaxies, like rogue stars?
Um,
Like it all seemed like they were all like kind of conglomerating together in a galaxy,
Mhm.
and like are there just stars that are just kind of sitting there, just not attached to anything?
Yeah, great question. And yes, the answer is yes. One of the questions is, could you even form stars? So first thing, first answer is that in general, galaxies need stars need a galaxy to form in. They're sort of like the pressure cooker to pull the gas together and make the stars. Once they're formed, they can kind of do whatever they want. And we think that some small fraction of stars do tend to get ejected by their galaxies. Stars will interact with other stars and get thrown out. And we've even found what we call alien stars from other galaxies passing through our own galaxy that we think were ejected out. And planets around those stars, so like alien planets from another galaxy. And there's even some situations where we think stars can even form outside of galaxies if you get colliding gas clouds just right. But yeah, so the answer is yes, and those are exciting to look for.
How did your students look for the galaxies in the app? Was it random, or how did they find them?
Oh, yeah, no, it wasn't random. It was basically using the one discovery as a template for new ones. We just said, okay, we know what this one's properties are like. We know what it looks like. Let's just go find ones that look pretty similar to that. And what that has to do is measuring the brightness of the object, what we call the color of the object, is some of the properties of the stars, how fuzzy and basically how big it looks on the sky. And found pretty much very quickly found one that was like almost a twin of the first one. And we haven't gotten lucky with another one like that since. So we were hoping to find more and more of them. We found a few more, but nothing quite like that first discovery.
You showed an animation of two galaxies colliding or interacting with one another, and it looked like a very violent kind of interaction.
Mm-hmm.
What's the chance of that our galaxy interacting with another galaxy like that?
Yeah, it happens all the time. So for the galaxy, it's violent, but for the us living inside of it, it's sort of like, I don't know, if your house collapsed, the ants might not even notice, right? So we wouldn't necessarily notice. In fact, the latest thinking is that the Andromeda galaxy, which I showed at the beginning, is on a collision course with the Earth. In fact, I think some of that comes from that I showed that satellite measured the motions of the stars in the Milky Way, also measured the motion of that Andromeda galaxy, so you can figure out what trajectory it's on. It looks like it's going to collide with us in a few billion years and then merge together into this giant elliptical galaxy. But the Earth would probably not really notice because the space between the stars is so big that they all just kind of fly by each other. Now, we might get unlucky. You might trigger a blast from the supermassive. The supermassive black holes will merge as well, and that might trigger some sort of radiation outburst, which might fry us potentially. But again, that's a few billion years from now. I think we have time to figure it out.
Thanks. This was really interesting. I'm trying to sort of wrap my head around how do you get an orientation? So, for instance, here we are on Earth, so we could be the center of the whole everything. Or in your field, are there certain ways that you pick locations that everything else is defined from, in terms of trying to orient things that you see?
Well, okay, one thing is what's called the Copernican principle. So this goes back to Copernicus, this idea that the Earth is not the center of everything. And that persists in being a fundamental assumption built into astronomy now that there is no center to the universe. It does kind of look like that. It looks like all the galaxies are expanding outward from us. And it's sort of just it's a kind of an illusion. I'd have to go into some details about how that works. So there isn't really any center in terms of like setting a reference frame. You can sort of you have these things called quasars, which are really distant. They're basically supermassive black holes, which are emitting this enormous amount of radiation, so you can see them all the way across the universe. So that sort of amounts to a quasi-fixed reference frame, and that's the best sort of reference frame we have for measuring the motions. When I show those motions of the stars in the Milky Way, you need some reference frame, and that's what we use is those those distant black hole quasars to set the reference frame.
So you showed us this spectra in terms of the visible light.
Mhm.
And of course, there's electromagnetic radiation all across above and below the visible spectrum. Are there any areas that of electromagnetic radiation that we just can't see, but we know are emitted, that are sort of invisible to us because we can't observe them, but we know are there?
I don't, well, question is, you could always go to infinity in either direction and have the longest, infinitely long or infinitely short wavelength. Question is, do those actually exist in practice? I think scientists have become very clever at filling in all the gaps. You got from the highest energy gamma rays, and there are ways of detecting those. I don't think there's any gap there, all the way to the lowest energy radio waves. That's where there might be a gap. There might be radio waves that are so long that we couldn't detect. I'm not an expert on that, but I imagine, actually, you've got an expert sitting next to you. Andrew might be able to talk to you afterwards and tell you if there's some that we can't detect or not. But you could get a radio wave that's sort of the size of the Earth, and that would be difficult to detect, for example.
Hi.
Hi.
You mentioned at some point being able to look into the past,
Mhm.
confirm something. Can you explain that?
Yeah, so that's the idea that, so anybody like baseball? Okay. If you sit in the bleachers all the way, past the outfield and you see the ball get hit, what do you see and what do you hear? There's a lag. So first you see it, and then a split second afterwards you hear the sound. Okay. So what happened is that the sound, you're sort of hearing into the past when you hear that sound. Like the light for us is effectively instantaneous, but you hear the sound later. So you're hearing into the past because it takes time for the sound to get to us. So you're hearing into the past. And again, with thunder and lightning, you hear the thunder after you see the lightning. You're hearing the lightning in the past. So the light works the same way, except it travels much faster, and it's very hard to measure that lag on the Earth. But when you get out to the scales of the universe, you start having that lag, which is a finite lag. So when you see the nearest stars, you're actually seeing 4 years into the past, and farther out until you get into billions of years in the past. Sometimes that's a nuisance. Sometimes it's a gold mine, because then you can actually see the early universe. Otherwise, how would we directly know what happened?
Maybe I have an outdated understanding of how black holes work, and you can kind of correct my misguided interpretation. But as you were talking about kind of toward the center of the black hole, where the stars are moving very quickly around the mass, I kind of imagine as black holes like sucking things up. Like, how do these stars not wind up getting pulled all the way into the dark matter, or like is there something different between dark matter and antimatter that consumes it, or like?
So one question is sort of why the black hole doesn't just suck things in. Is that what you're asking?
Yeah.
So that's the way gravity works. The short answer is angular momentum. And why? And it's the same question as why doesn't the sun suck the Earth into it? So and the reason is the Earth has momentum that the sun is constantly pulling. What's happening is if this ball is stationary and I pull on it, it comes right and hits me, right? But if it's moving and I pull on it, and it's trying to get away from me now, then it has its momentum which keeps it from coming back. And it's called that angular momentum. So if it's moving, now I am pulling on it toward me, but it keeps moving around. So that's this conspiracy between the two forces. There's kind of this fictitious force called the centrifugal force, which keeps it going outward, and my gravitational force pulling toward me, and it keeps it in a balance, and it keeps it in a circle. So that's what keeps the planets from falling into the sun, and it's the same thing that keeps anything falling into a black hole unless they get very unlucky. So basically, if you were to take the sun and collapse it into a black hole, we might not have to worry about the stock market anyway, but the Earth would not notice otherwise. The Earth would just keep going around the sun, black hole sun, just the same as it was before, because the mass has not changed. So does that help? No. And that was in that movie Interstellar, if anybody saw it. You sort of had to, if you wanted to go into the black hole, you sort of had to aim for it, because you wouldn't just fall in by accident. You have to aim for the black hole. Maybe in the back.
You mentioned that when two black holes collide, supermassive black holes collide, they might emit like a blast of radiation. Could you explain more about why that happens?
Well, it's a balance of energy. So one of the great conservation laws of the universe is energy is conserved. And so if you drop an object, then it's converting potential gravitational energy into kinetic energy and going faster. And so the black holes, when they collide, they're losing potential energy, and that has to go somewhere. First they're moving, it makes their motions really rapid, that's kinetic energy, but then they merge and they have no more kinetic energy. So that energy also goes out somewhere into, say, gravitational waves. Also, it can go into some electromagnetic energy, into these blasts of high energy radiation, gamma rays and X-rays. Also depends on what other material is around that can get heated up and blasted out. Is that sort of what you're asking?
So you were talking earlier about how the gravity changes how gravity possibly could be the reason for the dark matter.
Mm-hmm.
How does that work with the cosmological principle?
Which cosmological principle?
The one where you assume that the physical laws apply the samely everywhere in the universe.
Oh, right. So that's why we think that there's dark matter, because we know how gravity works on the Earth, we know how it works on solar system scales, and then we assume that unless we have a reason to think otherwise, it should be the same everywhere in the universe on galactic scales until we have some good reason to think otherwise. But one of the good reasons to think otherwise is we have yet to detect dark matter. People have been trying really hard, and I think some of the main classes of dark matter people are starting to give up on and looking for other classes. So that's getting a little discouraging in terms of like, why haven't we detected the dark matter yet? Although there is a lot of possibilities of reasons we might not have detected it, and that's a reason to introduce this other deviation from the normal law. Also, there's some mathematical reasons. You could write down Einstein's theory of general relativity. It's very nice and elegant, but you can add extra terms to it, and it's still mathematically correct. It doesn't mean that it matches reality. So those are some of the reasons why you might try those alternatives.
I think we have time for one more question.
Do you have a recommended reading for beginners, dabblers, and non-physicists?
I'm not up on the some of the latest books. You know, there's the classic Brief History of Time from Stephen Hawking. I know Neil deGrasse Tyson has a book out recently. Has anybody read that one? It's called The Universe for Beginners or something like that. I think anything, if you just go to a bookshop, if you can find one still, and look at the science shelf, there's a lot of high quality books out there. So just start anywhere that's got galaxies in it. Basically, all this is involving galaxies and supermassive black holes and dark matter around galaxies. Something that covers galaxies would have a lot of this information in it.
Thank you, Aaron. Please join me in thanking Aaron one more time.
Thanks. Thank you.